we talked, most of the class last time was about what do you do if you want to fit a logistic model and you have variables you want to control for, and you have exposure variables, and of course you have a health outcome. And the health outcome right now we're assuming is binary, 0, 1. We're then considering, well, what happens if you have more than a single exposure variable? What if you have 2 or more exposure variables? So when I talked about this using an example from the MRSA data set, I said that example fits into a more general model framework, which allows you to have as many exposures as you want to consider. In this case, Q of them, as many variables as you want to control for potential confounding, and then you have 2 kinds of interactions. You have exposures with variables you want to control for, and exposures with other exposures. So that's what that whole topic was talking about. And then the question is, how do you go about the process of coming up with the best model when you have this situation? And I tell you, many of you, I don't know whether it's going to be most of you, when you're doing your thesis will be in this situation. So that's something you have to be concerned about. Well, that is, if you're not concerned about it, then you're not going to do as good a job. So anyhow, so how do you go about this process? Well, there's a number of different ways to do it. And again, all I can possibly do is give what I think are reasonable guidelines based on thinking about it for quite a while. And they're guidelines, they're not rules, and I've given you 2 basic alternatives to way to approach this problem. And both alternatives start the same way. They start with variable specification, and then they follow with assessing interaction about the relationship between exposures and the variables you're control for. But then they differ. In steps 3, 4, and 5, they differ because in alternative 1, you assess interaction before you even deal with confounding. And in alternative 2, you deal with confounding before you consider anything about the E's, whether they're E's or just E's by themselves. That's the difference between the 2. Then I walked through some examples with the MRSA data with looking at both these alternatives. And I got to a point, now I'm skipping ahead, I'm not going to go through these examples again. I got to a point where when I looked at the second example, that is the second situation, which was alternative 2, we wound up, after I considered some different ways to look at the data and how you might think about it, I eventually wound up with a model that had the two exposures. So the MRSA data set that we were dealing with considered previous hospitalization and previous antimicrobial drug use, PAMU, as the 2 exposures, and there were 3 control variables, and the model we wound up with after looking at alternative 2 had no interaction terms, it had the 2 exposures, and it had only one of the 3 potential confounders in that model at that stage. And that was going through the process up to this point, and the next step, the last step in the process, would be assessing whatever you can conclude about the E's in this situation. Now, you don't have EEs, you've gotten rid of them. They were found to be not significant. That's what I say in step 4. So step 5, how do you deal with the E's when you've got a situation like this? And in this case, you've decided already that you're going to control for V2. You've gone through this process, this set of guidelines, and you know you're going to control for V2 because you've gone through that, and now you're deciding, well, what do I do about the E's? Do I keep them both in? Do I drop one of them? Do I drop both of them? Or what is the goal of the study was to describe the exposure-disease relationship where you had 2 exposures. And is either one or the other or both of them important determinants of the outcome? And to what extent are they determinants? What's an appropriate odds ratio to describe their effect? How significant is that odds ratio? And get a confidence interval around it to see something about the precision of that. So that's what you'd want to do. Now, where this led me to is I said, well, there are several alternatives to do this. And then that led me to say, well, maybe since we wound up with a situation where we knew we were already done with the V's and we have two E's left. The most general situation, and this is where I was sort of near the end of last time, most general situation that's similar to this is what if all you have is exposure variables, or essentially you're starting off, you didn't have any V's, or whatever V's you wanted to consider, you decided you're going to keep in the model, you're not even going to address whether they're confounders or not, they're in the model. But in this case, I'm saying suppose they're all E's. So in this example, suppose in the MRSA data set, all of the variables in that data set that was being considered were considered E's. You didn't know enough about any of them to be able to say, I want to consider them as variables I want to control for. Well, then this would be your starting model. If you wanted to consider the initial stage where you have to specify the model and you wanted to allow for the possibility of at least up to 2-factor product terms as interactions. Is that right? I mean, it doesn't mean you can't have other more complicated terms. I could have E1 times E2 times E3 times E4 times E5 in there. And if I wanted to consider that, I could. But I'm asking for trouble if I do that. And it doesn't mean that I may want to have trouble, but it's up to me to decide where I want to start. And the sort of a simpler way of doing it, in this more complicated situation, to start this way. But you notice that there are no V's in here. So how do you proceed starting with this situation? So I said, well, the first thing you do, if you want to follow along the guidelines, first thing you do after variable specification is interaction assessment. So that would mean you then look at these product terms and you decide which of any of these product terms need to stay in the model. How would you do that? Well, the way we talked about assessing interaction, regardless of what kind of terms you had in the model, was you did a chunk test, and then you did some kind of backward elimination to see if you can drop any of them, regardless of what the chunk test says. That's how you would do that. And once you get that, once you carry through that situation, you're done with the interaction stage. So suppose it turns out that, so that's what I'm saying. Do the chunk test for no interaction, followed by the backward elimination involving only product terms, and then keep in the final model, after you do this interaction assessment, any E term, any single E term, that's a component of a significant product term. You follow that? That's part of what we've been talking about so far. So what I've shown on this slide are two possible things that might have occurred if this was your starting model. There's more things that could have occurred. I'm just showing two things. One is some of the interactions were significant. So if it turned out that these two interaction or these two product terms were significant, since it involved E1, E2, and E3, that would mean E1, E2, and E3 would have to stay in the model because they're part of the product terms that you've decided have to stay in the model. But it doesn't mean that E4 has to stay in the model. So you can assess whether E4 maybe should stay in or maybe not, depending on how you go about the process. Now, if it turns out from interaction assessment you found nothing was significant when you started the chunk test and then you went backwards, then you'd be, if you started with this model, you'd be left with this model, which only has the E's in there, has no product terms. And you still have a question, a problem of, what do I do with this? Do I just fit this model? Do I do something else with this model? And one thing you could always do is backward elimination, but maybe could you just fit this model? So there are some alternatives that I want to talk about here. Okay. Now, and so what I've done here is, this is the second stage, interaction assessment. Second stage when you've got all E's. Okay. Now, the third stage in my modeling strategy that I've been describing to you is confounding precision assessment. And what I said last time and what I continue to say this time is that's complicated and it's sort of debatable how you would deal with that. Because when we talked about the modeling strategy when you only had a single E, confounding precision assessment had to do with the V's. It didn't have anything to do with the E's. Okay? Because we didn't know enough about the E's to even consider a DAG other than a DAG involving the E, it involved the V's. So one argument for saying that you shouldn't even consider confounding and precision when they're all E's is to say, don't do it. forget it. You don't have any V's in the model, so don't consider it. Another argument might be, well, maybe you can argue, depending upon the way you view things and depending on what you think you know about the literature, even though you know more about the V's than you know about the E's, maybe you can still figure out some DAG involving the E's in there that you still want to work with. Well, that makes this whole question very debatable, and it's, as I sort of said last time, it's complicated, and I put a discussion of this in Appendix 1, so I didn't want to spend any time talking about it, because if I did, we'd spend the rest of this class talking about it, and we wouldn't go as further along as I think we need to go anyhow. So as far as I'm concerned, confounding and precision assessment when they're all E's is debatable, and you can take it that way if you want. If you believe that you want to go further, fine. But you're not going to get, I mean, if you're worried about what kind of a grade you're going to get in the course, you're not going to get any questions about that, confounding and precision, when they're all E's that you're dealing with. So, depends. So, given that, and you've dealt with interaction assessment, now you're down to exposure assessment. So the exposure among the E's. Okay, so how do you do that? And there's several options. So that's what I want to show you. Now, first of all, let's look at the simplest situation where you have two E's, only two E's, E1 and E2. In this case, for the MRSA data set, that would just be those two variables, previous hospitalization and PAMU, previous antimicrobial drug use. And let's say we don't want to consider those other three variables, or we decided we're considering it and we're either not going to control for them at all, or we're going to control for them, but we're done with them as far as we're concerned. So we're only worrying about these two E's. That's our model, okay? How do we go about doing this? Well, there's different options, okay, and that's what I want to talk about. The first of them, there's there's 5 options I'm going to talk about. The first of them, and this is where I changed some of the slides. You know, I sent you an email and I said, sorry that I had to do this. And when I send you and I say sorry, you know, and I changed it, it's because I want to make something clearer than I thought they were in the notes. So I hope you aren't mad at me for sending you something like that, that you think I'm actually trying to help you by doing that. Maybe you're mad at me because, boy, he keeps changing it. Why didn't he change it 2 weeks ago? Okay? Some of you might have said that, to yourself, or last week. Well, we're all doing things. Last week I was worried about something else. Okay? So, okay, why didn't I do it 2 months ago before the class started? Well, I spent a lot of time forget it. I'm not going to talk about it, Anyhow. Okay, so here's the first alternatives. Basically, first of these alternatives. This first alternative just says, look, I got these two variables. We're done. That's your model. That's your final model. And I've got these, I've got 2 exposures. I want to see to what extent any one of them is predictive of the outcome. So what I'm going to do is I'm going to fit this model, and then I'm going to get an odds ratio for each exposure, recognizing that the other exposure is in the model. So I'm saying I'm getting an odds ratio for previous hospitalization, assuming I'm controlling for the other variable, and I'm getting an odds ratio for PAMU, given that I have previous hospitalization in the model. I get the odds ratio and the confidence interval, and then I try to draw some conclusions from that if I can. That's one approach. It's not easy to decide what to do when you're saying, well, this is important given the other one, and this is important given the other one, but what about by themselves? It gets a little, so this is one approach. It's not the only approach. And this is where I added a slide. Now, it turns out in the MRSA data set, if you actually do this, and these are the only 2 variables in the model, what you're going to get is the odds ratio for the effect of previous hospitalization, given that PAMU in the model, is 5. Pretty high. And the confidence interval is pretty wide, but it doesn't include the null value. So it's significant, right? And the odds ratio for PAMU, given previous hospitalization in the model, is also pretty high. I mean, it's not 1. It's not close to 1. It's 4.281. And the confidence interval also is wide, but it also doesn't include the null value. So what would you conclude about these 2 variables as to whether they're strong or reasonable predictors of the outcome if this is the approach you took? And you could say, well, I think they're both important. And if you have any one in there, there's the other one's still important given the other one in there. That's what this is saying. If I control for E2, then E1's important. If I control for E1, then E2 is important. So it looks like I can say they're both important, but what I'm not doing is I'm not considering how they jointly sort of affect the outcome. So that's one approach, but it's not the only approach. And that's what number 2 is, and that's the one I described to you when I was describing how you might go about this, the analysis process. Number 2 says, again, stop with this model. Don't try to reduce the model. You're going to keep these 2 variables in the model. But what you're going to do is you're going to focus on it differently. You're going to focus on the joint effect of these 2 exposure variables. If you had 4 exposure variables, you might deal with the joint effect of the 4, which is going to be more complicated. But with the 2 variables, one way to talk about the joint effect is consider how 2 specifications of the 2 variables in one situation might compare with another specification of these 2 variables in another situation. So this is the high, low thing. And you might say, well, this is maybe a reasonable way to consider how to do the analysis because this is the most extreme situation about these 2 exposures. Somebody has them both versus somebody has neither. If I don't find any effect there, I'm not likely to find an effect if I consider some mixture. But it doesn't mean I couldn't consider another mixture and I couldn't consider analysis where I actually try more than one of these and do an analysis. But now what I'm trying to say is, suppose I approach it this way, what do I do? How do I go about the analysis? That's what I'm trying to explain. What do I do with this analysis? This is another alternative. Stopping with this model, go about the analysis. Well, what it would mean is I'd have to come up with an odds ratio that considered however I'm going to specify the 2 ways I'm classifying these 2 exposure variables. What would that odds ratio be? Well, if this is the model, and it's binary, the E1 and E2 are binary as they were in this data set, then the odds ratio, as you can maybe figure out, because you are all experts now at computing odds ratios, no matter how many variables there are in the model, the odds ratio would be E to the what? What would the odds ratio for this situation? Well, if you look at the next slide, whoop, that isn't the next slide. You look at the odds ratio would be somewhere here. It would be E to the beta 1 plus beta 2. That's the odds ratio if you decided your way of trying to, evaluate the effect of the combined effect of exposures to compare high versus low. You're talking about this as your odds ratio of interest. That's the odds ratio that would describe that. Okay, so what you'd have to do is then fit the model, your logistic model that has these 2 variables, and allow you somehow in the output to get an estimate of this odds ratio, not just the individual odds ratio, the E to the sum. Well, you've learned how to do that, and I've written the code over here for how you might do that, because what you would do is, again, your model would be MRSA equals previous hospitalization and PAMU. Those are the 2 variables, the only 2 variables in the model, so that's the model statement. And then you'd have to have a contrast statement that you've already learned about. And the contrast statement, you have to give it a name. I'm calling it the sum because it's the sum of these 2, or it's E to the sum of these 2. And then I say the sum, and I say previous hospitalization 1, PAMU 1, estimate equal to EXP. This code is going to give me an estimate of this odds ratio in my data set, and it's also going to give me a confidence interval around that. That's what you've already learned. I'm just trying to show you what you would do. And if you do this, this is what you get as the output. You get 22.2534 is the estimated odds ratio of the combined effect of these 2 exposure variables if you decide you want to keep them both in the model. That's high. That's really high. And it's also very wide. The confidence interval is very wide. So it's a very sort of unreliable answer, but it's high. And you notice the confidence interval does not include 1 and the lower limit is 10, so it's very significant. And that's what your conclusion would be. You'd say jointly there's a strong combined effect of these 2, and that's the way I've carried it out. That's the way I've done it. So that's a second way to do the analysis. So what about other ways? Did you follow that? So I've just shown you what the output would be. I didn't have these slides on Tuesday. I wanted to add it to show you what the output would be, so it would be clearer. I don't know if it's clearer, but anyhow, I'm trying. Okay, then the third approach is to actually say, well, look, maybe we shouldn't stop with the model that has both of them in there. Maybe we should try to consider dropping one or more of these variables if one or more of them really doesn't need to be in there because they're not doing anything. I only need one of them. Or maybe I need both of them. So carry out the backward elimination approach to obtain a reduced model of E's that remains significant. Okay, that's what I would do. That's another way to do it, to see if I can drop one of them. Well, it turns out for this data, this is what when you fit the model that has these two in there, this is what the output looks like. It's got these intercept, the previous hospitalization, the PAMU variable, and it's got I'm only showing you the Wald chi-square values. I'm not showing you the likelihood ratio test value, which could be different, but they're not. And you notice that these two variables are highly significant on their own. So what it says is the test for adding previous hospitalization to a model that already has PAMU is highly significant. Adding PAMU to a model that already has previous hospitalization is highly significant. So what would you conclude about the backward elimination approach? Can you drop either one of these? And the answer is no. So your final model after the backward elimination approach is going to contain both these variables. And you could conclude it any way you want in terms of what I did in either step 2 or step 1, but this way I'm making a decision about whether I can drop one. And I'm saying I can't drop either one. So that's another approach, okay? So these are, well, now there's other ways. Now, another approach, which you learned in the linear regression course, is to actually do what's called forward selection. You remember what that was? Forward selection. That says you don't start with any variable in the model other than the intercept, okay? And then you see which of the variables you're considering. In this case, there's just two exposures, is the most significant variable, and is it significant? And if it is, the most significant and significant, you add that to the model first. And then what you do is, once you have that in the model, if you're adding something in there, you see if I can add the other one in there, or as many I have. So forward selection, you start with nothing in the model, and you see if you can add something. Well, that's rarely done unless when you try to do backward elimination doesn't work, or that the model doesn't fit. The model, you have collinearity or something and you can't do it. But backward elimination is more sensible because it lets you consider the most complicated model before it lets you start off with nothing in there. You may even never get to a complicated model if you do forward selection. So that's a point of view. But anyhow, that's another option, but it's rarely done. And then there's a fifth option. Carry out the BWCE approach. What's that? The backward change in estimate approach that I talked about in the last class. Okay, that's another approach. Now, remember, that's an approach where we looked at whether there was a change in the estimate, 10% change in the estimate, deciding to drop a variable, and then if we decided that this was the least confounder, we then go to the next variable to see if that's not a confounder, and we keep going that way. In this case, we only have two variables. Well, it turns out the reason why I don't recommend step 5 is because step 5 only looks at change in odds ratios. It doesn't consider statistical significance. So backward change in estimate approach doesn't seem to be reasonable to me as a different. So I would go with 1, 2, or 3. And again, these are points of view. And that's the way life is in terms of, when you really get down to how to do epidemiologic analysis, how to do analysis of data, not everything is just cookie cutter stuff. There's decisions you have to make. And they all, different people might have different points of view on it. And I'm just giving you my point of view, and it's a reasoned point of view based on thinking about this for quite a while. But it doesn't mean you couldn't have a different point of view. So if it's your thesis and you say, well, I heard what he said, and I don't like it, I'll do my own thing. Fine. Do your own thing. Write up what you say, or cover it up when you're writing your method section. Don't say what you did. Either way. But do whatever you want to do. But this is what I think is reasonable. Okay. So that's why I'm describing this. Okay. So now there's a problem with this option, though. There's a problem with the third one. The third one of the BWE option that I want to talk about. Okay. Problem with this. Okay. Here's the problem. Okay. Here's the model we're starting off with. And suppose we do backward elimination, okay? And suppose this results in dropping E2. Because what is backward elimination? We drop the least significant of the two variables given, now this didn't happen in this exam. I'm just saying suppose. That didn't happen. They were both significant. Suppose we drop E2, because that's less significant when E1 in the model than is E1 not significant when E2 is in the model. It sounds like I'm double talking here, but I'm saying suppose we drop E2 first. Okay, we're left with E1. Now, can we conclude from this backward elimination that E1 is really the only important variable among these two variables? Well, from backward elimination, that's the one we're left with. So you're tempted to say that, and a statistician might say, well, we're done, that's it. I don't need both of them, all I need is just, E1, E2 is not significant and it's the least significant one, so I can drop it. Well, debatable, here's why. So here's what I say. Suppose, in addition to the above results, that E1 is not significant, that, suppose in addition to my grammar's a little off here, but that E2 is significant in this model. Suppose it turns out that we have this situation. E2 is not significant given E1 in the model. But suppose it turns out E is significant in the model that just has E2 in there. Okay. In other words, E1 was wound up in your final model when you did backward elimination. Okay. And E2 would drop out. Okay. But what I'm saying, suppose, if you think about it, that maybe E1 was not significant in the model, and even though it was not the least significant one, it's not significant, so you can consider have drop that from the model, is what I'm saying. And then you're left with E2, and suppose E2 is significant. Then you might argue that even though backward elimination gave me E1, if I consider this other thing about what's happened when I look at the variables individually, well, maybe I shouldn't just say E1 is the only variable. E2 on its own does something too. So what I'm saying, what should you conclude about the effects of E1 for this situation? Is E1 the only important variable among E1 and E2? And I'm saying, my answer would be both E1 and E2 are important predictors on their own, but once you control for one of them, the other is not important. E1 is not necessarily the only important predictor. Now, do you agree with me on that? I'm saying if you don't even look at that, the individual contribution of a variable without considering, you're not even going to see that. And if you just do backward elimination, you're not going to see that. Okay? I don't know if you follow what I'm saying. Now, that's what I call situation A. Situation A is E2 is significant in this model and E1 is not significant in the model that you started off with, given E1 and E2. Now, here's situation B. I wrote this in, so it's situation B. Suppose in addition to the above results that E1 is not significant in this model, suppose it's also true that E2 is not significant in the model that when you drop, even though E1 is not significant, and you can say, well, maybe E2 might be significant. Suppose E2 is not significant when I consider it by itself. Well, backward elimination would say, I need to keep E1. But backward elimination, without thinking about it, without thinking about what happened when I consider E1 and E2, particularly E2, if E2 is not significant on its own, then the conclusion would be that only E1 is important, that E2 is not important. E2 is not important given E1 in the model, and it's not important on its own. That's what this statement says. That's what situation B. That's a different situation. Okay? So things are a little bit more complex than just doing backward elimination. So what all this means is that there are alternatives to how you consider this situation. When you have two, it's not simply backward elimination, although that's what you could do, but you might miss something. That's all I'm saying. You might miss something. And it's up to you when you're doing your thesis to decide to what extent you want to go through the trouble of dealing with this issue that I'm raising. Okay? That's what I'm saying. Okay? Now, Here are the alternatives if you're dealing with this situation and you want to consider backward elimination. I've considered other ones where you can keep both variables in the model. Well, one thing is you just carry out backward elimination and you don't worry about the problems I just raised. That's one alternative. That's what a lot of people do. Another one is you do the chunk test for E1 and E2, and if it's significant, you keep both of them in. And if it's not significant, you drop them. That's something we talked about when we talked about the chunk test. If you do the chunk test and it's not significant, what you might want to do is you might say, well, I don't need anything in there. If it is significant, I'll keep them both in there. But that doesn't allow you to look at the individual ones and what they do. So that's a flaw in alternative 2. Alternative 3 says, determine whether E1 is significant given E2, and determine whether E2 is significant E1, and then draw conclusions from that. Well, that's what I was doing without considering the variables individually. I was just considering one variable given the other and the other variable given the first one. And that's a way I could do it, but if I don't consider the variables individually, then I may be missing something. So alternative 4, and I said, you see, I wrote this, I like this one. This is what I'm saying, determine whether E1 is significant given E2, and determine whether E2 is significant given E1, determine whether E1 is significant without E2, and determine whether E2 is significant without E1, and then draw conclusions. To me, that's the best way to go about this thing, if you had two variables, if you wanted to consider backward elimination. Now that I've said this, and I don't know what you think about all this. You think, well, why is he going through this? Why? I'm doing it because if you have this situation, you have to worry about what your final model is and what's going in. There are different ways to think about it. Okay, now that leads me to the next thing. Suppose your reduced model after assessment looks like this. You don't have 2 of them, you have 4 of them in there. Okay? What are your options? What are your options? One option is, say, based on what I've said so far, one option is say, well, that's your stop with that model. That's your final model. And for that model, compute the odds ratio for each exposure given the other variables in the model and get their confidence interval and draw conclusions. That's what I started off with when I talked about you only had 2 of them. Well, if I have 4 of them, I could do the same thing. Instead of having 2 odds ratios and 2 sets of confidence intervals, I'll have 4 of them. And then I'll try to make sense of that. That's that's the alternative 1. Alternative 2 says, well, again, stop with this model, but then consider the joint effect of these 4 E's together rather than their separate effects. Now, what I'd have to do that is consider a way of specifying the 4 E's one way and a way of specifying the 4 E's another way. Okay. Now, if all 4 E's were binary, and I wanted to do something analogous to what I did when I had only 2, and they were binary, what would I do? How would I do that? Sort of looking at the extreme, what would it be? Be 1, 1, 1, 1 versus 0, 0, 0, 0. That's what I would do, and then I would get an odds ratio for that and see what it is and whether it's significant and get a confidence interval around it. That's how I could deal with this situation when I want to consider the joint effect. Okay. And the third situation is carry out backward elimination, and I say, but ignore the problems I raised earlier, which doesn't consider, well, one might not be significant given the others, but maybe it's significant on its own. That's one way to do it, and a lot of people do that. And the fourth alternative is to say, well, consider the problems I raised. It's much more complicated when you have 4 of them than when you have 2 of them. And if you have 4, you're going to have to worry about it more. You're going to be pulling your hair out more. I think, dealing with it, or you'll be coming to some methods person around to try to get some help. A lot of times that's me, but it doesn't have to be. Okay, so anyhow, so that's what I'm saying. If the reduced model after assessment is bigger, is more complicated, and that's really where I want to stop talking about several exposures. Okay, I'm saying there's a strategy for that. There's some guidelines for that. It involves 2 different kinds of interaction. How do you do that? And I got 2 alternatives. And then what if you have only exposure variables in there, you don't have any V's? I've talked about how you do that. Okay, and you take it for what it's worth, and when you've got your situation or you're asked a question in this course to do, then you have to deal with it. based on what we've said or based on anything else, any other way you want to do it, but you have to justify what you're doing. So, okay, so that's that part. Questions about this? I mean, this is complicated. Is it? It's complicated. Are you happy I told you about this? I don't know. Yeah, there's a question back there.
So I have a more philosophical question.
Philosophical. Uh-oh.
So when you're considering these two,
Yes.
you see that one has some sort of influence on your
Yeah.
previous antibiotic use is doing something. So, and that's a real life situation. Some people are aren't. Why would you take it out of your model if that is going to be having some type of effect? Why wouldn't you just consider making it a B?
Well, again, you have to think about where you are when you start the study. When you start the study, if you really, what you have to do is identify the roles that the variables play. To me, that's, you don't call it a C variable, to me, unless you have some reason to consider it's a C variable. That's from the literature, from what and if you think that, you make it a C variable, And if you don't feel like you know enough about it and your goal of the study is there's enough uncertainty about it, I want to make it an E variable, I make it an E variable. And then you have to take the consequences for what you're doing. That's my point of view on it. And it doesn't, can you keep changing around? Well, you may keep changing around until you get the answer you want. So that's a problem. So it's always a good idea to think what you want and do that. And then if you keep changing, well, then you might say, well, look, if I do it this way, I get one answer. If I do it this way, I get another answer. What's the best way to do it? Then you're going back to stage one again. Okay? I don't know what else to say. Okay? Philosophy. Right. Yeah. And philosophy, how do you interpret these things? I mean, it's not easy to do it. That's why there are different ways to do it. Okay, but interpreting it is not that is, I mean, I'm showing you how to do some of the mechanics in the context of some guidelines where it's not easy to define a rule, but then when you finally get your results and you try to make some sense out of it, well, that's another level of what you have to do. And I'm not that good at that because that's not I'm not a specialist in MRSA, or whatever it is. Okay, so with that, I now want to change gears, and I want to talk about the next topic, which is, see if I can find it, and it's this one, screening. Okay, screening. Let's see. Okay, that's the next topic. Okay, and the topic after this is Polytomous Logistic Regression. Okay, so can you find this somewhere? You got it. Okay. Now the thing I'm trying to say about this, there's the word screening may mean two different things to different people. I'm not talking about screening for disease. When people say, well, does he or she have a certain high level of something, and do they likely to have disease? We're going to send them to a special X-ray or MRI or something like that because we're screening. We're not talking about that. This is talking about screening variables when you're doing modeling, when you're trying to do mathematical modeling. Screening variables in the process of doing modeling. And in our context at this point, we're doing logistic regression. So it's screening variables when you're doing logistic regression. So that's what I'm talking about. Now, here's the situation here. Here's the question. What do you do when you have a large, now I'm considering the situation with one E. It's more complicated with several E's. So I want to just talk about one E. What do you do when you have one E and several C's? And the number of C variables is very large. And a model containing all such variables and maybe interactions involving them with the E becomes unreliable or it doesn't run. What I mean by it doesn't run is to mean you're not getting any answers out and you're getting some kind of an error message saying it ain't going to work. Okay? When it says becomes unreliable, that's going to be something that might result from your assessing collinearity, which we're not ready to talk about, and that when you find collinearity, you may find that, well, this model maybe runs, but there's something wrong with it that I think it means I can't trust the results of the thing and I have to do something else. But what if you get this situation, okay? Basically, it says, it looks like clearly if it doesn't run, you got to do something to make it run. I mean, you've got 20 variables. You try to run it with 20 variables, it doesn't run. And you wanted to control for the 20 variables because you've done your homework and you identified, as far as I'm concerned, 20 variables make sense in some way. And I'd like to, if possible, fit that model. Now, if I had 10,000 people in the study, maybe I could do it. If I have 1,000 people, maybe it wouldn't work and the model won't run. Okay, so what do? Well, what people often do when this happens is they do some kind of screening. And what I mean by that is they make a decision to drop some of these variables. If I have 20 variables, they may say, well, I'm going to drop some of them. I'm going to drop 5 of them for some reason. One reason for dropping them is, well, I thought about them, but now that I think about them again, I don't want to deal with them. That's one reason. That's a non-statistical reason, but it's a good reason. You know, you thought about it from the literature, but now that I think about it, I don't need that many, okay? But what I'm thinking is, suppose you do all that and you still have too many. So, and then how do you determine, do some kind of screening, or you can assess collinearity to determine which variables to drop. But once you do collinearity, you still may have this problem. You still may have too many variables, okay? So, and you can't do collinearity, as we'll see, after this midterm, or just before the midterm, but it won't count in the midterm. As we'll see, you can do collinearity and still have too many variables left. You can decide, but if you have perfect collinearity, you can't fit the model. So you have to do something. You have to drop something. But as I say, note, however, there are good ways and not so good ways to carry out screening. And that's what I want to talk about, good ways and not so good ways. Now, think about what people often do, and that's the next slide. Well, that's not the next slide. Here's the next slide. Now, I skipped something, but I'll go back to that. Next slide says, a typical approach, and I'm going to say let's call it method 0, is to screen out or remove from one's initial model those variables that are not individually significantly associated with the binary outcome. So I'm saying, suppose you're doing logistic regression. You got like 20 or 50 C's that you want to consider, okay? And what you're going to do, and you got 1E, okay? And let's assume you're not dealing with interaction. You could be dealing with interaction. Actually, you could want to deal with interaction also. So let's suppose what you do is you say, I'm going to look at each E one at a time and to see whether it's significantly predictive of the outcome on its own. And then any one that's not significantly predictive of the outcome, or I don't get statistical significance, I'm going to drop it. And that's how I'm going to reduce. That's method 0, okay? Who does that? Have you ever done that? Well, I don't know how many you've done research now, but I think some of you may have done that, okay? You don't want to confess to that, right? But, you know, at this point, maybe you don't know why. Whether you want to or not. But that's typically done. That's typically done particularly if you have a situation where all the variables you have in your model are exposure variables. You don't have variables you want to control for, you have exposure variables. And you might say, well, look, I got to get rid of some, I have too many of them, I'm going to drop the ones that don't look like they're doing anything on their own. That's what's typically done, and then you work with the reduced model. So it makes sense in that case. But there's a problem with that, okay? And let me go back to this here. Purpose of screening is to reduce the number of predictors being considered so that a reliable and interpretable final model can be obtained to help answer the study questions of interest. That's the purpose of screening, to reduce the model, to reduce the size of the model, the variables you're dealing with, so you can come up with an answer to your question, a reasonable answer, okay? Now, the two primary drawbacks to doing any kind of screening is that, first of all, if you drop some variables, you're not doing what you wanted to do. I mean, the reason why you identified 20 or 30 or 50 C's was because you thought they were all reasonably important, and if you decided that you didn't want to drop them for some kind of reason that they don't make sense at some point, then you're saying, I really would like to control for them together, and I can't do it. So if you try to drop some of them and just drop a bunch using screening or whatever, then what you're doing is you're not doing what you wanted to do, is consider them all together. So you're not going to accomplish what you wanted to do. That's a drawback, okay? But you're trying to get something done, which is a positive thing. And the other thing is there's no guarantee, as I say, that one's final model contains all the relevant variables of interest. When you do this screening thing, there's no guarantee that what you've done is the right thing. You're just making some decisions as what variables to drop based on some reasonable things, reasonable decisions. So there's a problem with screening. There's some problems, but it's something that you often have to do if you have too many variables. That's what I'm saying. Are you there? Are you here? I don't know. Okay, so that's method 0. Method 0 says you deal with these variables one variable at a time. Okay, now questions to ponder. I don't know where I came up with that word, ponder. First of all, is there anything that can be criticized by method 0? Is there anything wrong with that? And the second question sort of relates to the first question. Should the use of method 0 depend upon whether your predictors are a mixture of E's and C's, only involve E's, or only involve one E and several C's? That's the second question. Third question is, how large does K, the number of variables in your model, the number of C's, have to be relative to N in order to justify screening? Well, the third question doesn't really have a great answer. Nobody has a good answer to that. So that's it for the third question. What other ways are there to carry out screening, and when, if at all, should they prefer to the typical approach? That's what I want to talk about. And where does collinearity assessment fit in with this problem? Well, I'm going to answer the fifth question, and then I'm going to talk about, most of what I'm going to talk about is number 4. And the fact is there anything, I'm going to talk about a little bit all of them right now. Is there anything that we can criticize in screening? Yes, there is something, okay? And it does depend upon this. The answer to question 2, should they use, the answer is yes, okay? And what other ways, that's what I want to talk about. Now, where does collinearity assessment fit in? Well, it may be, if once you learn about collinearity, if you can fit a model, the model actually runs and you can fit it, it may be that collinearity will help you get rid of some, but not all of them. And so once you do collinearity, you may still have too many left, and then when you have too many left, you still have to do some screening to get rid of some more. And once you get rid of some more, you may then say, okay, I'm now going to go back and look at collinearity again. So you may do collinearity twice. Once before to drop some that you might save from dealing with screening, do the screening, and then see if you still have a problem with the variables that are left. Okay, so now, here's my answers. Yes, method 0 does not consider confounding or effect modification when assessing variables one at a time. That make sense? Why doesn't it consider that? Why did I say that? Why doesn't it consider confounding or effect modification to decide how to drop variables from the analysis? Say that again? N? Because you just include all the models. Well, that's not what I'm doing. This method 0 says I drop the ones that aren't statistically significant. That's what it says. So I'm going to drop some if they're not statistically significant. I may not include them all. Okay, but the problem is, we learned about how do you assess confounding? You don't do a statistical test. What are you doing here? A statistical test, right? So you're getting rid of a variable without really seeing whether it's a confounder or not, even on its own, by itself, right? What about, where does interaction fit into method 0? What's wrong with method 0 in terms of assessing interaction? Are you assessing interaction? Does method 0 allow you to get an interaction? No. So that's the problem. If you use method 0, it's not really exactly right because you're not dealing with what you worried about, these variables you're worried about for, the reason why you're worried about them. So what do you do instead? How do you do something that's different from method 0 that would deal with this? Well, here's the answer to this, sort of. Let's talk about confounding. Suppose you're talking about a variable, one variable at a time. You're just talking about one of these C's, okay, one of these C's, and you're going to look at it one at a time and see whether it's a confounder of the exposure-disease relationship. You have one E and one D, so see whether this variable on its own is a confounder. How would you do that? Okay, in terms of, if you're doing modeling, you could do it using stratified analysis. If you're doing modeling, what you would do using logistic regression, you'd fit two models. You see the two models I've written here? One model has C in it with E, and the other model drops C. And what did I say? Confounding is present if we conclude that e to the beta, which is the odds ratio for the effective exposure, depending on whether C is in the model or not, is meaningfully different, more than 10% different in some sense. That's what you would do. That's what you do. That's not a statistical test. You could do that with each one of the 50 variables you're worried about. And you could check whether any one of those 50 variables, and you are dealing with confounding and not doing a statistical test. Of course, you're doing them one at a time. You're not doing it simultaneously, but you're sort of stuck with that. That's what I'm saying. You want to do it simultaneously, but you can't do it. So maybe you could do it two at a time or three at a time. That's more, but if you want to do it one at a time, which is what's often done, this is the way you'd want to assess confounding. Okay? What about interaction? Will this allow you to assess interaction about the given C? And the answer is no. It only deals with confounding. Well, if you wanted to see whether C on its own was an effect modifier of the exposure-disease relationship, what would you have to do? I mean, this is just common sense, given what you've already learned about logistic regression and what you've already learned about confounding and interaction. It's bringing it together. Okay? So here's the next slide. Okay? What did I do here? I now have a model with E, C, and E times C, right? What would I do with this model? Now I'm looking at just this one C, and I've got 50 of them. What would I do with this model? I want to see if C on its own is an effect modifier. Well, with this model, I would test for the significance of the product term, right? And if it's not significant, I'll say on its own, it's not an effect modifier, right? That's what I would do. And I'd look at I'd look at how meaningful the interaction is too, but but in any case, I would evaluate the interaction. This model would allow you to assess interaction. Okay? So I've now shown you how you can assess interaction and how you can assess confounding. Now, how do you put them together? You have 50 variables. You want to decide a process for screening the 50 variables. You don't want to do testing, because I'm saying that's not dealing with these problems of confounding and interaction, but you want to do something along the lines I just described. How would you do it? Okay, what would you do? What would be the process? Well, what you might do is you might take each one of the variables, one at a time, okay, just like I did. The first thing you do is assess interaction. Remember how interaction before confounding? Remember that? First thing you do is you see whether any one of these variables is an effect modifier on its own. Whatever it is, age, whatever the variable is an effect modifier on its own. You test for E times age in the model, okay? So suppose you find it's not an effect modifier. Do you drop it? Do you drop it? Nobody said anything. Do you drop it, yes or no? How many say yes? This is a clicker. How many say yes? Do you drop it? How many say no? A few people who went like this. Well, it's really strong, And the answer is no. Why don't you drop it? Because it might be a confounder. Thank you very much, Emily. A few people. Thank you. It might be a confounder. So you decided on its own it's not an effect modifier, but it might be a confounder. So then what you do is after you do this, you then go back to this one for that C. Okay? Now, what if you found that it was an effect modifier? At first I said, what if it wasn't? Then you assess whether it may still be a confounder. What if it was an effect modifier? Well, then you keep it. Because on its own, if you got interaction on its own, it doesn't mean it's going to wind up in the final model that you wind up when you put everything together. But it's a way of you saying, I've got reasonable information to think that maybe this is an effect modifier when I consider it on my own. Okay, so that's what you do. Okay, so depending upon what you get here when you do interaction, You either stop if it's significant, or you go on and look at confounding. And then after you do all that with all 50, you're going to wind up with a subset of the C's that are either an effect modifier or a confounder. And hopefully it's a subset. If you went from 50 to 49, it's not going to help very much, but that's what you're hoping is going to happen. Okay? And so, now, what do you do if you have all E's? You don't have any C's. Well, then it's a different ballgame because you're not dealing with confounding, you're dealing with interaction. You might worry about interaction. You might look this with each one E against the other, but you're not going to talk about confounding in terms of the fact that you don't have any V's in the model. Okay, so that's what I'm saying. So that's screening. That's my message about screening, basically. There are some other questions I had. Should the use of method 0 depend on whether your predictors are a mixture of E's and C's, only involve E's, or only involve one E? The answer is yes. That's what I've been saying. Method 0 makes most sense when the model only involves E's, but is questionable with both E's and C's. That's what I'm saying. Okay, so I'm done with that. Okay. Now I want to go to the last thing, which is the topic for today. Right? So how far am I going to go with that? Okay. Did I do that too quickly? I don't think so, but that's my choice. Okay, Polytomous Logistic Regression. Okay, that's what we're going to start talking about now, and I have about 25 minutes to talk about it. Okay? Okay? Can I do it? Well, if you talk fast enough, you can do almost anything, right? But I want to explain it if I can. So Polytomous Logistic Regression, what is that all about? Well, first of all, I'm going to use it in the context of an example. There was a student, a PhD student in our department, I can't remember her first name, Anetka Volkova, and she did a study about end-stage renal disease, ERSD. What's that? What's that? That's when people have a kidney problem, big, serious kidney problem. The kidneys aren't functioning, and what happens if you have that? You typically go for dialysis, right? And it's not fun, okay, if you're in that situation. So it's a study in end-stage renal disease. Now, I got a bunch of references in here, and you notice one of the references says Ananth and Kleinbaum. So this is a guy that has been the chair of a department in New Jersey. He's gone on. But anyhow, and this topic is actually written, this example is written in your applied regression book. It's written up in your applied regression book. It's not written up in the logistic regression book you have, but most of you have the other book, unless you sold it or got rid of it. I don't know. How could you sell it? No. Polytomous Logistic Regression Overview. Okay, so here's the overview. First of all, you've learned linear regression, when the model is a linear model and the outcome's continuous. You've learned logistic regression, when the outcome is binary, 0, 1, only two possibilities. And you've learned about how to deal with logistic regression even with matched data, and when you have matched data, you might have to deal with conditional logistic regression. So if you learn this, okay. Now we're talking about what happens if the outcome has more than two categories. More than two categories. Not just binary, it has at least three categories. So the simplest situation of that polytomous logistic regression is just looking at a crude table where you have an outcome that has three categories. You have a disease, and they're either in this group or that group or that group. Okay, they're in one of three groups. One of three categories of disease. And if it's none, mild, and severe of a certain disease, those categories are what? They're ordered, right? If it was none, mild, and severe, those categories are ordered. Now, if you have ordered categories, there's another method that we're going to learn next time. I'm sure we're going to finish with this one. And we're going to learn next time, which has to do with ordinal logistic regression, when the outcome variable is actually ordered, has an ordering to it, okay? But this is assuming, suppose you don't have a natural ordering, okay? And you've got three categories, and suppose you have a binary exposure variable. This is the simplest table you could have, binary exposure, but now it's not a 2x2 table, it's a 3x2 table, okay? And you could have this kind of table in lots of different strata, and you could have lots of other variables you want to control for in addition to the variables that you're stratifying on. And so more generally, you could have more than 3 categories. You could have an exposure variable, which has more than 2 categories, and you may want to control for a whole bunch of variables. But this is what Polytomous Logistic Regression is about, just very simply, more than 2 categories. Okay, so that's what it is. Okay, so here's the example. Okay, the Volkova example. Again, it's an end-stage renal example data set, paper published from it, so on. And here's the question: data obtained from a surveillance system on about 3,000 patients with ESRD who initiated dialysis in Georgia, 2002, and she finished in 2006. This is her dissertation topic, okay? Now, the question of interest has to do with the exposure variable is race, and the outcome variable is cause of end-stage renal disease. That's the outcome variable. And there are 3 categories. Cause is hypertension, the cause is diabetes, the cause is something else, okay? Those are this is the exposure variable, and this is the outcome variable. And there are 2 variables to be controlled. One is how old were they when the dialysis started, and whether they're male or female. Those are 2. It could have been more, but this is the situation. Okay. Now, what does this mean? What does this mean? Race on cause of end-stage renal disease. What the concern is whether, for example, if you're black versus if you're white, whether the cause of the renal disease that you have, the non-functioning kidney, the cause may more likely be hypertension if you're black than it might be diabetes. That's what's being, is the cause of the disease going to more likely be one thing than another depending upon whether you're black or you're white. Now you notice, for example, African Americans tend to have higher hypertension than Caucasians. Okay, so you might think that there is an effect of race with respect to hypertension, but now there's 3 categories, not 2 categories. Okay, so what do you do with this? Okay, that's the question. Now I'm not sure you fully understand it, and I was on the committee, so I had to learn something about it. But now what you do, in this case, there's 3 categories of the outcome: hypertension, diabetes, and other. Okay, and when you have 2 or more categories, what you have to do is just like you typically do in any situation, even when you have exposure variable. This is the outcome variable. The outcome variable has more than 2 categories. Okay, and what you typically do is you designate one of the categories to be your referent category. Now, typically, as I said, the choice of the referent category can be arbitrary and is at the discretion of the researcher. And depending on what you do, you can always work with it one way and then try it another way, and you'll pretty much get the same conclusion as long as you recognize how you've switched things around. So it doesn't usually matter, but you want to make a choice. As I say, changing the reference category does not change the general structure of the Polytomous logistic model, but does change the interpretation of the parameter estimates because you've changed around what you're calling the referent group. Okay, so here's what the data looks like, the crude data for these people. Now you notice 3,049? That's the people in the study. Okay, and I've got hypertension, diabetes, 3 categories of the outcome, and black or white. Okay. Now what if I look at the in the total? I add them up. I get the total, and look at these numbers. Odds ratio 2.105, 1.4841. What's that? How did I get the 2.105? How is that gotten? What's that the odds ratio of? Hypertension versus other. So how is it computed? This is just crude. 630 times 395 divided by 323 times 366. That's how you got 2.105. How do you do 1.484? 773 times 395 divided by 562 times 366. So you're getting three odds ratios, but the one at the bottom is just the odds ratio of the reference group with itself. So that doesn't, there's nothing there. So you're really getting two. So the thing that you notice is you have three categories and you're getting two odds ratios, right? One of them is hypertension versus the reference group, and the other is diabetes, each one with the reference group. So let me ask you this. Suppose you had six categories, not three. How many odds ratios would you have? Oh, good. Okay, so that's what it is. You have 5 odds ratios that you have to do if you're doing polytomous. Okay, so that's what you do. And when you run this model, the model to do it, the model is going to give you 5 odds ratios and it can control for other variables. You just have to know how to run the model and how to look at the output and make sense out of it. And it's not that much different than the model that you're going to get and the output that you're going to get when you only had a binary outcome variable. Okay, so now here's the thing. Now look at what I've written on this slide here. So I've written the form of the polytomous model for the crude ESRD data. And I've written, what have I actually written here? Have I written just one model? I've actually written 2 models, haven't I? I've written 2 statements, 2 logistic-like statements, haven't I? 2 of them, okay? But actually, when you're doing polytomous logistic regression, these 2 are actually combined to state the model. The polytomous logistic model involves these 2. Any one of them is not the polytomous, it's just it's relating race with the reference group. But the 2 together is a polytomous logistic regression model because it allows you to consider it together, okay? Now, you notice that it's the crude, so what's not in here? The variables I mentioned to control for, like age at initiation and gender, sex, aren't in this thing because I'm talking about the crude. If I wanted to consider the variables age and gender, what would I want to do? I'd add them to the model. That's what I did down at the bottom of the screen. I added age and gender to the model. Now you notice, you see age, it says age G. What does that mean? What does the G stand for? Age group, okay? And you notice it says from 2 to 7. So what does that mean? These variables in the model are dummy variables for how many groups? 2 to 7. If there were 7 groups, right? So 2, 3, 4, 5, 6, 7. So there's 6 variables. 7 groups, 6 dummy variables, right? That's what's being done here. There are 7 age groups, and then there's gender. So this would be the model for if you wanted to consider age as a group as opposed to a continuous variable. Okay. Now let me ask you this. Suppose you fit this model, and you got estimates of let's talk about the crude thing. You got estimates of alpha and these 2 alphas and these 2 betas. Okay, what would you do with that? What would you do with what you'd focus on is the betas, right? Because the betas have to do with odds ratios. So if you got a beta 1,1 and a beta 2,1, and you got beta 1,1 hat and beta 2,1 hat, and you got numbers for them, and then you exponentiated each of these betas, what are you getting? You're getting odds ratios in this model for the effect of race on the outcome, given that you're comparing hypertension to the reference group, and this is race to the outcome, given that you're comparing, this is not hyper, this is diabetes, and this is hypertension. Okay, that's what it is. Okay, now, in fact, if you fit this model, okay, so I've already told you sort of how you do it. I haven't shown you output yet, but if you fit this model, suppose I said, and I'm saying it here, suppose you wanted to test whether there's, in this model, this combined model, whether there's an overall effective race in this combined model. You see the null hypothesis I've stated over here? Beta 1,1 equal beta 2,1 equals 0. Because if they're both equal to 0, what does the model reduce to? A model that doesn't have race in either one of these 2. So if you wanted to test for the overall effect of race here, the test would not just simply be beta 1,1 equal to 0 or beta 2,1 equal to 0. It'd be that they're both equal to 0. What kind of a test is that? Is it a wall test? Well, what you've learned is it's a likelihood ratio test. You'd have to compare. What model would you have to compare? Well, I've shown it on here. You'd have to compare this model to this model. See the model at the bottom? Isn't that the reduced model? That's the reduced model. It doesn't have race in it. Under the null hypothesis. So you would get, and you get the difference in these log likelihood statistics, and why would it have 2 degrees of freedom? Because there's 2 betas you're testing. So, I mean, this isn't that hard, if you think about it. It's just, you've got more than just one odds ratio you're dealing with. If you got 3 categories, you got 2 odds ratios. 5 categories, 4 odds ratios. That's what it is, okay? So, okay, now, here's the output on the bottom of the screen here. Here's the output for the crude data, Look at the output over here. See, it says intercept, intercept, race, race. Why has it got 2 intercepts and 2 races? Why is it 2 lines for intercept, 2 lines for race? Because you got 2 intercepts and 2 coefficients for race. So that's why the output's going to look like this. Okay, that's what it's going to look like. Okay, and then when you go e to the beta for the betas, which are the 2 race variables, you're going to see 2.105 and 1.484, which is exactly what you got when I didn't even do logistic regression, when I just looked at the crude data here. I get the same answer for just looking at the crude analysis as I get when I do logistic regression, because this is a crude polytomous model. Doesn't have anything else in there other than the variable, the exposure variable, which happens to be race, and there happens to be not a binary outcome, and happens to have 3 categories. So what you see is 2.105, 1.484, you can see as confidence intervals. What about the test? Is race significant? How do you do that? How do you do that test? Well, it's a likelihood ratio test. You compare the -2 log maximized, -2 maximized likelihood for the model. This is your full model with the model that doesn't have these 2 variables in there. And the model that doesn't have these 2 variables in there is the intercept-only model, which the computer gives you -2 log L, 6534, and for the intercept and covariates, when these things are in here, 6091.865, you take the difference between these 2, you get 442 with 2 degrees of freedom, highly significant. Okay, that's what happened. Okay, so there's a highly significant effect of race on cause of end-stage renal disease when you consider it as a polytomous outcome variable. And you can look at the individual things, but you've got an overall statement about what's going on. Okay, now, next slide. Next slide is what happens when you add age and gender to the model. Well, what are you testing if you add age and gender to the model? Well, you're still testing whether race is a significant predictor, but now you're controlling for 2 other variables. So your null hypothesis is still whether these 2 coefficients of race are both equal to 0. It's just that you got other variables in there. So your reduced model is, your full model is this. Your reduced model, what do you notice in the reduced, what's not in the reduced model? What variable is missing from the reduced model? Race. Why is it missing? Because that's what you're testing. Under the null hypothesis, the race variable drops out of the model. So you're comparing this model with this model. This is the reduced model. There's no race effect. You still have these variables in here that you're controlling for. So that's the reduced model. So what is the computer going to do? Well, first thing the computer is going to do, what it's going to do, it's going to give you, for this full model, it's going to give you a fitted -2 log L. But you see this says the intercept-only model? Is this the intercept-only model? No, because it doesn't just have an intercept, it has other variables in there. So you'd have to fit the reduced model. It turns out in the reduced model, the -2 log L is not this, it's 6236.806. You subtract one from the other, you subtract this from this, and you still get something significant. Yes, this is Sobia. Ooh, I've tried enough, but this, yeah, Sobia. Last slide. The reduced model is what you get under the null hypothesis. The null hypothesis is that the coefficients of the exposure variable, and there are two coefficients, are equal to 0. So under that, you wind up, the race variable drops out of the model. So that's the reduced model. So what you... Why did I say it like this? Why did I write it like this? It was just shortcut. I'm just trying to say that this is for, why did I say that? Okay, why did I take it out? Well, maybe I should, that's a good point. Why, since I took it out, why is it in there? Good point. Okay, this is, N told me something, and I think I'll take it out. It's good question, good point. You know, in some sense, you're trying to get at this effect, but really it shouldn't be in there. It's not in the model. Very good. Okay, good. Okay, anything else like that? Yeah, okay. Okay, we're almost done, but I want to show you one other thing. There's a bunch of things I could show you, but this is what happens when you run, a couple of things. This is what happens when I run that model, the model with all these six age dummy variables and gender in the model. So there's 2 gender variables, and there's 6 times 2 age variables in the model, but I still have intercept, race. So you see the 1.0652 and the 0.5745. What's the odds ratio for the effective race controlling for age and gender in this model? It's e to this one and e to that one. This is a no interaction model. Now, I could worry about interaction, but I'm trying to make it simple here, not dealing with interaction. So it turns out that e to those coefficients is 2.901 and 1.776, which is not the same thing as what I got when I used the Crude data. When I used the Crude data, I don't know where it is, e to the thing was 2.105 and 1.484. Well, it changed a little. It didn't change much because they didn't have that much of an effect to control for them, but it changed a little bit. I mean, this 2.901 is not 2.5 something because we're now controlling for these other variables. Okay, so that's what you do, you know, and you could do this test, and the test is significant. Now, here's the last thing. Well, I don't want to, this is the general form of the model. Maybe I'll do that at the beginning of class next time. But here's what I want to, this is the form of the odds ratio, general form. Most of you can figure this out, but I'm going to make sure I go over it next. This is what I wanted to show you. How do you do this? Using Logistic. That's what I want to show you. How do you do it using Logistic? Well, Logistic, data equal Volkova. That's the name of the data set. Descending, usual stuff, right? Model, CERSD. That means categorical ESRD variable, you know, in 3 categories. And then it's got only one variable in this model, race. And in this model, it's got race, and it's got age, G, and gender. And you notice there's a class statement for age, G. What does that mean? Dummy variables for the age. So that's how I fit the second model, okay? And then you notice there's one other thing that's different from what you've seen when you did Logistic before, when you did just the, whether it was for matching or no match. What's different is there's something that says / link equal G logit. See the link equal G logit? You put that in, and then it's doing Polytomous. That's the key difference. Put that in. That's all it is, okay? Is that hard? No, it's not hard. What are you going to get? You're going to get more than one odds ratio, and you're going to get an overall test, and you can look at the effect of each odds ratio. So Polytomous is not that hard, if you think about it. Ordinal's a little harder, but it's not that much harder. In fact, I added another slide to this, and I didn't put it up on your slideshow, but you'll be seeing it next time. This is the code for Polytomous. This is an example of the code for Ordinal, with a different data set, okay? You see it says Logistic, descending, data, and then it's got class, it's a different variable, and it's got a different model with different variables in the model. What don't you see in the model statement that you see here. What you don't see is G-logit. You don't see G-logit. So when you're doing ordinal logistic regression, you do almost the same thing. You write the same code, and we'll talk about this next time. It's the same code, and you don't put G-logit, and the computer will know that you're doing ordinal logistic regression if it turns out that your outcome variable has more than 2 categories. It'll know that it's doing ordinal. Outcome only has 2 categories, you're going to be it's no different. But it'll be doing ordinal logistic regression. That's what we talk about next time. So in a sense, we did Polytomous Logistic Regression. Did it in half an hour. Was it the worst thing you've ever? No. The stuff we did before was worse. Right? Okay. See you on Tuesday. Thank you. Hi, now you are
I'm Katie Ross.
Katie Ross.
My
Caitlin?
Catherine.
Catherine.
I have a question about screening.
About,
Screening?
yeah, let me first
Okay.
get this ready to go. You want to stop it.